Well, hello, chemistry students. This is Mr. Kinney here. I'm going to go over the second half of our chemical bonds review packet for you. So this will be questions 31 through 51. And we should have gone over the first part in class, but I'll also have that one set up. So let's start right over here with question 31. Let me make sure to get this zoomed in for us. Oh, wrong way. Okay, I hope you can see that there. So question number 31 is going over there. Okay, I've got my pens. Okay, I'm set. So let's see, what do we got here? When hydrogen forms a bond with a halogen, what type of covalent bond is formed? Is it going to be polar or nonpolar? So, well, this is going to have to do with electronegativity. So we've got our chart that we have in the textbook that shows the electronegativities. And also, when we subtract those electronegativities, we get a number value, and that will tell us over here what type of compound it will tend to be. So let's see. When hydrogen forms with a halogen, what type of bond? Well, I'm just going to pick a halogen here is fluorine. There's also chlorine, bromine, and iodine, but I'm just going to put fluorine on there. So what type of covalent bond is going to be formed? Will it be polar or nonpolar? Oh, I'm zoomed off the paper there. Let me zoom. I got to come in a little bit. Sorry. Now, just a reminder for you. What polar means is that you're going to have on the molecule, whatever it looks like, there's going to be that slightly positive end. This is delta here, which kind of has the shape of looks kind of like a slanted S. And the oxygen here, okay, there's a hydrogen, there's an oxygen, and the oxygen here is going to be slightly negative. Okay, so that means we got a polar compound. Now, if we have something like two hydrogens bonding together, what's going to happen with them is that since they're the same element, they have the same electronegativity, there's not going to be a positive or negative side. So it's going to be nonpolar. Okay, so there's no partial positives or negatives on a nonpolar. So now let's get back to our question, number 31 here. So what type of bond forms? Well, we're going to probably, more than likely, I'm thinking we're probably going to get a polar, because when we look at the electronegativities for fluorine, it's 4.0. Again, electronegativity is the tendency of an element to attract an electron. And hydrogen over here is 2.1. Now remember, don't get distracted. Even though hydrogen's over here with the metals on the metal side, it is not a metal, except in the core of Jupiter by theory. So when we subtract these two numbers, we get 4.0 minus 2.1. And let's see, I can make that a 3, a 10, that'd be 9, 1.9 if I did my math right. So please help me on that. So when we take a look at this chart, so 1.9 comes out to be right in this area over here. It is a covalent bond, so we knew that, and it's very polar. Because what's going to happen is, now if we take a look at that, we're going to have the hydrogen over here, and it's going to be attached to the fluorine, and fluorine is very electronegative. Almost all the electrons are going to spend almost all their times over. Occasionally one will fly over there, but it's mostly going to be over there. And we had this from our notes, a diagram here showing a hydrogen fluoride molecule. The arrow here indicates the direction that electrons are moving. This shows us that this is the plus side, and then there's our lowercase, our delta is showing this is partially positive, partially negative. Number 32, what is the chemical formula when calcium? So when you take a look, calcium on the periodic table bonds with oxygen. Now, you've got your polyatomic ion chart that you can be using, but you know what? I don't want you to be totally reliant on that. Calcium is over here in group 2 of the periodic table. It's right there, which means it's got 2 valence electrons, which means it's easier to get rid of those 2 electrons. And when it does, it'll have a +2 charge, because now it's going to have 2 more protons than it has electrons, because it's lost 2. So calcium is 2+. Oxygen over here, when you take a look at its Lewis dot structure, it's like that. It's going to gain, it'll happily take those 2 electrons from the calcium. I'll make these X's here. And when it gains these 2 electrons, it'll be -2. So this has a -2 charge. And let's see, what is the formula? So now we can do crisscross, CaO, with its plus 2, and it's minus 2. We bring the 2's down like this. Now we got to be careful because it's not going to be Ca2O2 because we can both divide those by 2, reduce them down to calcium oxide. So that would be the proper formula for calcium oxide. And then now this is going to, since this is a metal and a nonmetal, that is going to be ionic. That is our definition of an ionic bond. List the characteristics of covalent molecules. Well, covalent molecules can be solid, they can be liquid, they can be gas. I think I can zoom in here since we're got small paper here. Okay, they do not conduct electricity. Don't conduct electricity. They tend to have lower boiling points, boiling and melting points. Now, ionic compounds, on the other hand, they tend to be, they're solid, they are crystals when solid. And what that means is we got our models we made in class. This would be representing sodium chloride. The big ones are going to be the chlorine. The smaller ones are going to be the sodiums. And we've got this repeating pattern because as they dry up, as you have the aqueous solution drying up, the very negative, this is a negative here, I don't have a marker to read. So you got the negative is being attracted to here, to the positive cation. So this is an electrostatic bond. It's extremely strong. In fact, it's the strongest bond there is. And with ionic compounds, it's very difficult to break that. So they're crystals when solid. They will conduct electricity when they're liquid or when they're in a liquid phase. So conduct electricity when liquid, or if they're melted, which I guess is a liquid, okay. And let's see, I think that was pretty much it. Oh, high melting point and boiling point. It takes a lot of energy to melt or boil as opposed to covalent bonds. And let's see, now we're switching over here. And let's see, so what is a crystal lattice? Oh, there we go. So crystal lattice, well, here's our model of it again. And again, a crystal lattice is just when we have positive cations attracted to negative anions and they begin to dry up, they're going to be attracted to each other. And what happens is, though, even though this might be sodium chloride here, when they form the crystal structure, you're going to have another sodium attracted to this chlorine, and it's going to have a chlorine there, you're going to have a chlorine there, you're going to have a positive here. And what happens is you get this repeating pattern. Oh, that should be bigger. So you start to build up this interlocking crystal structure, and which we end up, we made that in class, here's just a small section of that, is that these are interconnected to each other. So you don't just get sodium chloride, just that little one right there. They're going to be interacting close to each other in a big grouping. Why does it form? Okay, it forms due to the strong electrostatic attraction. Now, electrostatic, that's basically meaning that as opposed to like electricity, which is moving electrons, these guys really can't move, so their electric charges draw them together, but then they're kind of like they're unmoving once they're next to each other. So electrostatic, very strong, strongest of the bonds. What type of bond forms this structure? Well, that's going to be ion, so ionic. And what holds the atoms together to make this shape? Again, it's going to be the electrostatic attractions. And they say this ends up having a very high lattice energy, but it's electrostatic attractions that do that on there. Let's see, what's number 35. What is the Lewis dot diagram for carbon dioxide? Well, I'm going to do this first off when we go to draw this. You know, we start off, this is what carbon looks like. Oxygens look like this when we draw them out. Okay? So what I'm going to do is, I'm going to redraw these though, because see, I want to get it so these unpaired electrons are near each other. So I'm going to scoot this over, and let's use a colorful pen for this one. I feel like turquoise. So carbon's going to be in the middle. Now what I'm going to do is just, I'm going to draw its Lewis structure like that. I'm going to just kind of put it slightly sideways just to make it easier to see. I'm going to put oxygen over here. So we got 1, 2, 3, 4, 5, 6. I'm going to put the paired electrons out here. Okay, oh, that looked like that was. So what's going to happen is, okay, so these two will team up and share electrons. These two will team up and share electrons. And when I draw the line like this, that's going to represent that they're sharing these two electrons. We're going to have another oxygen that's going to be over here. 1, 2, 3, 4, 5, 6. These electrons will pair up, and here's another pair that will team up. So what we end up with is we've got, if we look over here, we've got 2 pairs of electrons being shared. That means 4. And we got another 2 pairs of electrons being shared. Now, I'm going to clean this up. If we were to do this with Lewis structures, it would look like this. There's those 2 pairs. Again, this is just tidying it up. So it would look something like that. And then what we can also do is you may see it that when you have these paired electrons, we'll connect them together, that you may see them drawn like that. So that would be the Lewis structure for carbon dioxide. Now the question here says, why do water molecules stick together? Well, water molecules, they're going to stick together because they're polar. They are polar, which means they have a partial positive side and a partial negative side. Let me zoom in here. Got a diagram of that here for you. So this is from our notes. So if we take a look at this, so we've got the oxygen with a higher electronegativity sucking the electrons towards it, makes this partially negative over here, and then this is going to be partially positive over here. And then what happens is they tend to stick together because, now first off, if you interpret the question as what keeps this molecule together, okay, well there's, they're sharing electrons, you got covalent forces holding together, but I'm interpreting the question as why are these two molecules stuck together, are attracted to each other, and it's the hydrogen bond, which this hydrogen is attracted to this negative part of this other water molecule. And that's a factor that makes water drops ball up. So did I answer it? They are polar, so they have a positive and negative end. And so you end up with your partial positive hydrogen over here. It's attached to the partial, or attracted to the partial negative part of another water molecule. Describe hydrogen bonds. Okay, well, we're kind of doing that. So hydrogen bonds, they're not truly a bond where electrons are being shared. It is hydrogens are attracted to partial negative charges. And again, the best example is going to be, like I showed here, you've got the partial positive of this hydrogen partially attracted to this partial negative. It's a fairly weak bond, but it's enough that can hold the DNA helix together, and it can keep water, when you dump water on the table, put a drop of it, it looks kind of like this. It beads up because they're attracted and makes this little network over there. 38. If SO4 has a net charge of -2, okay, now SO4 is a polyatomic ion. So I'm going to put parentheses around this to show it's going to stick together, and we're saying it has a -2 charge. So it's it becomes it's an anion there. List one element that would bond to it in a 1-to-1 ratio. So let's come back over here. So -2 is our charge. So we talked earlier that calcium creates a +2 charge, and any element in the alkali earth metals will form a +2 charge. So beryllium, calcium, magnesium, strontium, barium, and radon would do that. And you, if you look on your chart of polyatomic ions over here, we can see, all right, we need to find other things that are +2, and here's a whole bunch of them. So, and remember, like when you see manganese Roman numeral 2, that means it's manganese with a +2 charge as opposed to maybe one that's got a +1 or a +3 charge. So you can look on this chart as well and see here, because see like here, lead in this case is lead 2, but lead can also be lead 4 depending upon which of its valence electrons from its d orbitals it's sharing and switching around. So one element that can bond with it, well, I'm not going to give you one there. those guys right there, any of those would bond in a 1-to-1 ratio with that, plus the ones we saw in the polyatomic ion chart. What is so special about carbon? Well, okay, here's what's special about carbon. First off, it can make the most chemical bonds. It can reach out. It has a valence number of 4. That's a pretty big deal. Plus, because of its location, it's the lightest element. So silicon can do the same, and germanium to extent, and some of these other ones. But carbon, because it's so light, it can make a really, it's lighter to make a lot more bonds, but also it's got a higher electronegativity than these other elements here. Remember, as we go down the chart, the electronegativities get smaller. So carbon's got the highest electronegativity, and it can make 4 bonds. And there we go. So it can make up to 4 covalent bonds. So if we were to take our friend carbon here, and let me do hydrogen. Oh, we'll do hydrogen in red here. So, you know, we can team up with a hydrogen, another hydrogen, and you end up getting, I'll have to put that right there. So you've got this. If we were to rearrange that, you might see this drawn like this. Carbon, and then it's got the dashed lines. And again, anytime you see a dashed line, 2 electrons are being shared. And if you forget that, then put little bumps at the end of these lines, and those tell you, hey, there's 2 electrons that are being shared there. List the 7 diatomic molecules. Diatomic means 2 atoms, and our memory clue on that, okay, there's 7 of them. So start over here at atomic number 7. That's nitrogen. And we're going to make the number 7, ironically, we're going to make it out of 6 of them. Or I guess since this, okay, so there's, these here can be diatomic, meaning you can have N2, O2, F2, Cl2, Br2, and iodine 2. Now, the last one, because here's only 6. The other one is over here, is hydrogen. It can form H2. So those are the 7 diatomic covalent bonded compounds that we can have. So just remember this 7 right there, and you'll be in good shape. Define malleability and ductility. Malleability means it can be bent with a hammer. Let me see, I prepared, here's some salt, an ionic compound. Here's copper inside of there, a metallic compound. And salt is not malleable, okay? It's just not. Look at, boom, look at that. It just shattered into 722,322 pieces, okay? So it's not malleable. Let me get rid of that. Now, but you know, metals are malleable. I mean, you can bend them. Well, first off, yeah, you can bend them. I mean, look at here, okay? Okay, I mean, oh, okay, there's lunch is starting now. Sorry, don't be afraid by the bell. Look, I'm bending this, okay? It's taking a while. I don't want to destroy my desk, okay? But it's malleable. You can hit it with a hammer and it bends. The second part, ductility, means that you can draw it. Basically, it means you can draw into wires. Okay, there's probably a fancier definition, but we can stretch this and bend it and shape it into different uses for us. So that's let's see, malleability. Oh yeah, we can hit it with a hammer, it bends. Okay, and you can bend metals. That's because they've got those sea of electrons out there in metallic bonds. They can adjust quite easily. Okay, so let me clean up that. That was fun. All right, next one. What determines when a bond will be polar covalent or nonpolar covalent? All right, what it really comes down to on this is that it's going to be, if they're polar and covalent, that means that they're going to have their electronegativities that make up the 2 elements are, there's a big difference. So big difference in electronegativity. Okay, I'm just going to abbreviate it there. Big difference in electronegativity. So, pretty much, these elements on the left side of the chart tend to be lower, and these tend to be higher. So if you're going to be polar covalent, it's going to be like hydrogen and oxygen. Different sides, very polar. Now, nonpolar and covalent, well, that would be great examples, would be one of our diatomic elements. We can take H2 or we can take N2. All right, so H2, I mean, if you take 2 of these, they both have the same electronegativity. They're not going to pull one electron stronger than the other. So, nonpolar covalent. Oh, same thing over here, though. If you can take fluoride, you could have fluoride attached to itself. They both have a high electronegativity. They're both going to share evenly. So let's see. So what determines? So on this one, if their electronegativities are very close to each other, they will be nonpolar, like Br2. Okay, bromine diatomic molecule. They have high electronegativities, but they're both the same. They're both pulling the same. Describe number 43. The bonds between molecules and solids, liquid, gases, strongest to weakest. Well, first off, the strongest is going to be in solids, because it takes a lot of energy to pull those compounds close together, despite their electrons are trying to repel. So highest energy. Liquids would be next. They would be mid energy, because they are still really close. In fact, if we were to, a lot of times we tend to draw a solid as the particles really close to each other in a locked pattern. It takes a lot of energy to lock them in that pattern. Liquids, okay, liquids are going to be close too. I'll draw this in green, but they're not in a particular locked pattern. They can flow around each other. There's not as much energy binding them as there is in the solids. And then gases, they are far apart from each other. They're very weak forces holding these together. Because they can fly apart, they're not next to each other. So it takes more energy to have something in a solid state of matter than it does in the gaseous state of matter, because it takes forces to pull these together and bring those electrons next to each other. Okay, now for review, this is before. Mass number, what's the difference between mass number? Okay, mass number is neutrons plus protons. Atomic mass